Welcome all, this is yet another video in topology series, and this will see compact spaces, before which we'll define open covering, which we'll need to define compact spaces. Covering is actually a collection of subsets of topological space X which covers space X, and they are said to cover space X if their union is equal to space X, and if every element of collection is open, then that covering is said to be open covering. For example, if we consider topological space R, then collection A1, if considered containing integers, rationals, irrationals, then it is the covering of R, but it is not open covering, as set of integers is closed set. Similarly, if we consider A2 as a collection of open interval minus infinity to 0, open interval minus 1 to 5, open interval 2 to infinity, then this set or this collection is actually covering, and in fact it is open covering of R, because each and every element of this set is open and this collection covers the entire space of real line. Similarly, if we consider A3 is equal to collection of open intervals minus n to n, such that n is any natural number, then this collection is also open covering of R, since every element here also it is open. Also, union of all these open intervals will also be open, and here A3 is actually infinite open cover of space X. If we consider A4 is equal to collection containing open interval minus infinity 2 and open interval 2 to infinity, then this is not a cover of space X, as the element 2 is not getting covered. Now we will head to definition of compact space. Space X is said to be compact space if every open covering of space X has finite subcover. For example, space R is not a compact space, since if we consider open cover equal to the collection of open intervals minus n to n, such that n belongs to natural numbers, then union of these intervals will cover space R. Now this is open cover of R. Let on contrary that this cover has finite subcollection, that means finitely many open intervals from this collection covers space R. That means union of open intervals minus ni to ni for I is equal to 1 to k is equal to R. This means for some maximum m between all ni's, the open interval minus m comma m is equal to R, which is a contradiction, because m will be a finite number. Space R is not finite. Thus R is not a compact space. Now if we consider set or collection containing elements 1 over n, such that n is natural number union with singleton 0, then this space is compact space. We'll see how it is compact. For this, consider A be any arbitrary open cover of set S, then there will exist open set containing 0 and it should be of the form open interval minus 0.1 comma R intersection with S. Now open interval minus 0.1 to R will contain infinitely many points of set S, as 0 is limit point of the set. So only finitely many elements will remain out. Say k number of elements remains outside, so k number of open intervals will cover those k points. So we require only k plus 1 number of intervals to cover spaces, and so S is a compact space. Any finite space X will also be compact space. Closed and bounded subsets of R will also be compact spaces.